All right, you guys, here we go. Today we're taking on properties of tangents. So I'm giving you this pretty cool picture right at the top. Here I have an image of a person who is throwing a discus. So let me just write that this is a discus throw, kind of like a shot put. All right, so here we see the person who is kind of anchored down right about here, let's imagine. Okay, and then they rotate their body a full 360 degrees, and then they release the discus like that. So that release point is this point right here. And in a moment, we're going to call that the point of tangency. So looking at the relationship between the tangent line, remember that a tangent line is a line that touches the circle in one location and its radius. So here in my picture, I'm going to draw in first my center. So about like so, there's my center. Okay, I know that this line right here is a tangent line. So I'm going to label it as such. And when I draw in a radius, so remember that a radius connects the circle to the center. So any point on the circle connected to the center, and any one radius will always be congruent to any other radius in the circle. So here I have in the center of my circle. This right here is one radius, but I'm interested in that one radius and how it connects to that tangent line right here. So it connects right in that location. So this location is called our point of tangency. I lost my N. Tangency. All right, so there we go. So we have our tangent line, we have our radius, we see that they connect at the point of tangency. And most people are able to see what the relationship is going to be. We're going to see that the radius and the tangent line, they are perpendicular at that point of tangency. So if a line is tangent to a circle, then it is perpendicular to the radius at the point of tangency. Okay, in a plane, if a line is perpendicular to a radius, okay, so a radius of a circle, at its endpoint on the circle, then the line is tangent to the circle. Okay, so again, a tangent line, right, intersects the circle one location, so one point of contact. And when we connect our radius to that point of tangency, we should see a perpendicular relationship. So in example 1, we're looking at a tangent line and a radius, and we're trying to solve for x. And I'm saying leave all answers in simplified radical form. Let me slide it up to here. All right, so in the first one, let me first just draw in the right angle, because again, a radius and a tangent line are perpendicular at that point of tangency, like so. Okay, and I'm trying to solve for x, and x is a radius of my circle. So I can see that from here to here, that's also a radius. That would also be x. Okay, I'm going to draw that picture off to the side, just a little bit stripped down, right, just so I can focus on my parts. So I can see that this leg is x, this leg is 15, and the hypotenuse is x plus 9. So now I'm just using a whole bunch of Pythagorean Theorem to solve for my unknown value of x. So I know that Pythagorean Theorem tells me that a squared plus b squared equals c squared, right? The a and b are the two legs, and the c is my hypotenuse. So here I could say that x squared plus 15 squared equals x plus 9 squared. Okay, and then here I need to write this out as two separate packages because I'm saying x plus 9 times x plus 9. So my next stage, I have x squared plus 225 is equal to x plus 9 times x plus 9. And that's a good reminder that we're going to have to FOIL this out. So the first, the outer, the inner, the last. Okay, so let me, again, one more step. I have x squared plus 225 is equal to, well, my first part here is x squared. My outer is plus 9x. My inner is plus 9x. And my last is plus 81. So now I'm just going to combine my like terms, clean it up. X squared plus 225 equals x squared plus 18x plus 81. Okay, so in looking at my equation, it might look like I have a quadratic equation, but if I subtract x squared, say I subtract it from this side, it will subtract from this side as well. So really, those quadratic terms are going to cancel away, and I have a nice linear equation to solve. So from here, I'm going to take away the 81 from each side. So I get 144 is equal to 18x. Okay, and from here, I'm just going to divide both sides by 18. And I'm going to end up with x equals 8. Okay, next up, here another variation of the skill. So again, I'm able to see that I have a right triangle, right? Because I have a tangent line, I have a radius. They are perpendicular right there where it connects at that point of tangency. I can see that a radius here is 20, so here is another radius right here. That has to be 20 as well. So if I use that same strategy, first I'm just going to draw out the triangle as its own separate entity. Here I have 20, I have 21, and here I have x plus 20. So here I'm going to go back, I'm going to use Pythagorean Theorem again. So I'm going to say that 20 squared plus 21 squared equals x plus 20 squared. Okay, and then again, I need to see that as two separate packages. So I'm going to go ahead and multiply this out. I have 400 plus 441 equals x plus 20 times x plus 20. And again, I'm going to have to FOIL this out. Okay, I'm going to keep just working to clean it up. I get 841 is equal to my first x squared, my outer plus 20x, my inner plus 20x, and then my last plus 400. Okay, again, I'm just going to combine my like terms. So I still have 841 is equal to x squared plus 40x plus 400. Okay, from here, I can see that I do have a quadratic equation. I want to gather all of my terms on one side and have my equation set equal to 0. So I'm going to take away the 841. So 0 equals x squared plus 40x minus 441. So from here, I see it's a quadratic equation. When I think of my options for factoring, or my options for solving an equation, factoring comes up as one of the primary methods that we've been using. But if I think of the other options, sometimes we solve quadratic equations by taking the square root. Sometimes we factor. Sometimes we use quadratic formula. Another method that we use is to solve by completing the square. Okay, in our class, we've really been focusing a lot on solving by factoring. We've also been focusing on solving by taking a square root. So square root wouldn't be appropriate here simply because I have that linear term in the middle. So I'm going to try to factor this. So when I factor it, what I'm visualizing in my head is a product and a sum. So my product is the A times the C. So I'm looking for a product of negative 441 and a sum of 40, right? That B that's right there in the middle. So again, I'm thinking of ax squared plus bx plus c. So the a times c, right, that's my product. And then the b, that's the 40, that's the sum. So here I'm thinking, well, what two numbers can multiply to negative 441 that add to 40? So take a moment, see if you can factor it. You might pause this video to see if you can factor it. Okay, and then unpause. We should come up with negative 9 and positive 49. So 0 is equal to x minus 9 times x plus 49. So when I set each factor equal to 0 and I solve, I get that x is equal to 9. I also get that x is equal to negative 49. Okay, and when I think about this, if I was to plug back both of these values in, I can see that, well, the 9 makes sense, but the negative 49, well, that wouldn't exactly work. I can't have a negative measurement. So my only solution that works is that positive 9. Okay, let me slide this up just a little bit so we can get to the next example. All right, here we go. So my next one, here again, I'm just going to draw in that right angle right here. Sketch my diagram off to the side. So here's my 5, here's the 8, and the whole hypotenuse is my x. Well, that's an easy variation. So now, Pythagorean Theorem, I have 5 squared plus 8 squared equals x squared. So 25 plus 64 equals x squared. So x squared will equal 89. I solve by taking the square root this time. And I'm looking for any pair that would multiply to get us 89, and I don't see any. So I know that x technically would be plus or minus the square root of 89, but I can't have a negative measurement, so I'm only interested in the positive square root of 89 as my final answer. All right, next up, here again, I see that I have a right triangle. There's that right angle. My radius and the tangent line are perpendicular. Okay, and I can see a radius that's marked as 2, so this part here would have to be 2 also. So again, good strategy, just drawing that triangle off to the side. So here I have 2, here I have 4, and here I have x plus 2. So here, if I use Pythagorean Theorem again, I can see that 2 squared plus 4 squared equals x plus 2 squared. So 4 plus 16 equals x plus 2 times x plus 2. And I gotta FOIL it out. So now I have 20 is equal to, first, x squared, outer, plus 2x, inner, plus 2x, last, plus 4. So 20 is equal to x squared plus 4x plus 4. So again, I see a quadratic equation. I want to have it set equal to 0 so I can try to solve it. So I'm going to take away the 20. So 0 equals x squared plus 4x minus 16. So as much as I search for it, if I try to go through my list, run through my list, I can't solve by taking the square root. I can look for something that's going to multiply to a negative 16 and add to 4, but I'm not going to find it. So I have to use another method. And another method that we use all the time in Algebra 1 is we go back to the quadratic formula. So let me write that for you right here. So your quadratic formula. So here, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So first, if I just define what a, b, and c are, I'm just going to carry on up here. So a is the quadratic coefficient, so 1. B is the linear coefficient, so 4, and C is the constant, so negative 16. So if I plug into quadratic formula, I'm going to start with x equals negative b, so negative 4, plus or minus the square root of b squared, so 4 squared, minus 4 times a, 1, times c, which is negative 16, all over 2a, so 2 times 1. So as I clean this up, I get negative 4 plus or minus the square root of 16. Now this is always a place where I see mistakes. So this whole part right here, that's a package right in there. So if I multiply that out, I'm going to get positive 64. And then all over 2. So x equals negative 4 plus or minus the square root of 80 divided by 2. And the square root of 80, I can simplify that a little bit more because that's 16 times 5, so 4 root 5. So I'm going to end up with negative 4 plus or minus 4 root 5 divided by 2. Okay, and if I'm going to simplify that down, well, I'm looking at the 2 should go into both of those items here and here. So I'm going to end up cleaned up with negative 2 plus or minus 2 root 5. So those are my two possible solutions. But again, if I have negative 2 minus 2 root 5, that would give me a negative value up in here for a measurement. That's not going to work. So I'm only interested in the positive, which would be negative 2 plus 2 root 5. That is my final answer. All right, flip it over or go to that second sheet. Let me just adjust my papers. Okay, so here, the question that I'm posing is, well, how could you show that line AB is tangent to the circle? And if we're trying to show that it's tangent, we just need to show that there is that perpendicular relationship at point A, that point of tangency. So really, all we need to do is show that the Pythagorean theorem is true. So Pythagorean theorem must be true. Okay, so looking at my picture, I can see that if O is my center, this has to be a radius as well. It would have to be 5 units. So this whole portion here would be 13 units. So Pythagorean theorem again, a squared plus b squared equals c squared. So I'm trying to show that that's a true statement. So is 5 squared plus 12 squared equal to 13 squared? So is 25 plus 144 equal to 169? Well, absolutely. 169 is equal to itself. Check. So here we're just confirming that line AB is tangent to circle O at point A. Right? We've verified that there's that perpendicular relationship between the tangent and the radius. Okay, next up is the radius and chord theorem. So here first, let me just draw in a radius. So here's about the center of my circle, and here is a radius. Okay, and then what I want you to picture is I want you to picture that tangent line that we had initially. So let me draw a tangent line that we saw on the other side. And picture that we're taking that tangent line and we're dragging it down into the interior of the circle, so it becomes a chord. So let me draw in purple, sliding it into the interior of the circle, just like so, so it becomes a chord just like that. So if we're building off that tangent radius relationship here, right, and we have that right angle right in there, it's sliding down to the inside of the circle right here. So I'm going to put a right angle in this slot right here. So if a radius is perpendicular to a chord, which is what we have right here, what we should identify then is, see that purple chord, it's being bisected, it's being split into 2 equal portions here and here. So if the radius is perpendicular to a chord, then the radius bisects the chord. Okay, so one more example, example 3. Let me slide it up. So refer to circle C. So if I call it circle C, C is the center of the circle. So first I'm saying name all sets of congruent segments. So I can see that, well, if C is my center, then I have a radius here, I have a radius here, and I have a radius here. My radii are all congruent. So I know that segment CP must be congruent to segment CS, must be congruent to segment CR. Right? All of those are congruent. They're all radii, And I know that radii are always congruent when it's the same circle. Any radius will be congruent to any other radius. All right, then I also know that since I have a radius here and I have a chord and they're perpendicular, then I know that the chord is being split into two congruent parts. So I know that PQ, that segment right here, will be congruent to RQ over here. That's the chord that's being bisected. Okay, then I'm saying, well, if PR, so if this whole span is 8, what would PQ be? Well, PQ will be half of the whole. So if PR is 8, then I need half of 8 to get me to 4. Right? Half of 8 gets me to 4. So PQ has a measure of 4. Note how I'm switching my notation, right? I'm no longer talking about the segment itself. I'm talking about the measure of the segment. Okay, next up, I'm saying if CQ, if right here CQ is 10 and PR is 24, find the radius of the circle. So here I'm just going to draw out a right triangle. It's all about right triangles. So let me sketch out one of those two right triangles. And here is where the C is, the Q, and the P. So if I know right now that CQ is 10, let me label that 10, and I know that PR, this whole span is 24, so split that in half, and PQ is 10, and I'm solving for a radius, well, that's just right here. That's the hypotenuse of my triangle. I'll call it X. So here again, I'm just back to Pythagorean Theorem. This whole section is about Pythagorean Theorem. So 10 squared plus 12 squared equals X squared. So 100 plus 144 equals X squared. X squared equals 244, solved by taking the square root. So if I simplify 244, I can see that it's 2 and 122. And then here I have 2 and 61, and then I get stuck. So I have a pair of 2's. Technically, X is plus or minus 2 times the square root of 61. But I can't have a negative measure for a radius, so my radius will have to be just the positive 2 times the square root of 61. All right, lastly, so if the radius of circle C is 9, so that means that this is 9, this is 9, this is 9. And QS, so if this sliver right here is 1, find PR. Okay, so let me draw again one of those two right triangles and label that this is the C, this is the P, and this is the Q. So I know my radius is 9, so I know that this span right here is 9. Okay, we're told that this part right here is 1. Remember that from here to here, that's a radius, so that's 9. And if that's 1, the difference means that would be 8. So right here, CQ is 8. And I'm trying to find PR. So I want PR, but I can solve for PQ. And once I have PQ, I just have to double it. So I'm going to call it X. And I just want to remind myself that I have to double it to get to my final answer. So for PR, I know that that will be whatever PQ's measure is, but times 2. So I'm going to solve for X, but then I'm going to double it. So back to Pythagorean Theorem. So I know that 8 squared plus X squared equals 9 squared. So 64 plus X squared equals 81. Take away the 64. So X squared equals 17, solved by taking the square root. X could technically be plus or minus the square root of 17, but it's a measurement. I'm only interested in the positive, so I get square root of 17. Okay, but again, I need to double it. So I could either take the square root of 17 and add it to itself, which would get me 2 root 17. I get the same thing if I just multiplied the square root of 17 by 2. So PR, what I'm asking for, PR, is going to be equal to 2 times the square root of 17. All right, and that's it. Hope you guys have a good day.